Hello, ladies and gents. Oh, hopefully everyone can hear me and you can all see my screen and everything okay. Welcome to our... Can you see my screen and everything okay? Oh no, welcome to our... Can you see my screen and everything okay? Let's turn that off. Sorry about that. I obviously didn't have my sound muted for some reason. But hello, welcome to A-level chemistry. This is our A-level class on lattice enthalpy and Born-Haber cycles, which is a lot of fun, actually, I think. Anyway, it's a bit like a puzzle, which I find quite fun. But welcome to our class. If you want to say hi, please do say hi in the chat. The more you guys interact, hopefully the more you'll get out of this. So yeah, please say hi in the chat. It's nice to see people here, so welcome. If this is your first class with us, welcome. If you're back for another one, then welcome back. Nice to have you back again. Really nice to have repeat watchers. That's always good. Oh, hello. Oh, I'm going to have a go at pronouncing people's names. You have to apologise. I will apologise in advance. Pradhuman. But hello, welcome. Hi, Tarek as well, and Mohammed. Hi, Fiona. Hi, Tabor. Nice to see you guys. Nice to have you guys in the class. We're going to be going through lattice enthalpy and Born-Haber cycles in a second. We'll just give ourselves a couple of seconds just to kind of sort ourselves out. Oh, hello, Renee as well. Welcome. Nice to have you guys here. This is one of our Sunday sessions. So we do Sunday sessions for the A-level sciences and maths. And this is our chemistry one. We've actually got another one next week, if my memory serves correctly. So we can have a look at the timetable for others later. Are you guys all A-level students, or some of you GCSEs just trying to get an idea of what A-level chemistry is like? Or is anybody... I assume everybody is year 12 going into year 13, because this is, summer holidays. So I presume it's A-levels going year 12 going into year 13, but you might be year 13 just brushing up on your knowledge, ready for chemistry at uni. Who knows? Going into year 13. Nice. Hi, Yusra as well. Welcome. Nice to have you in the class. Fabulous. So what I'm going to be trying to do is trying to get you guys as engaged as possible in giving me answers and things. So hopefully you guys are super quick. Oh, hi, Eddie as well. Going to hopefully get you guys doing some super quick typing and giving me answers as much as possible. And I will try my best to keep looking back at the chat and checking if you've got questions, please feel free to ask. If you want to answer each other's questions, that's also brilliant. Hi, Geraldine, nice to have you. Yeah, so please answer each other's questions as well if you think you can. That's absolutely fine. And when I notice a question, I will confirm an answer, or we can have a chat about the answer on all of that sort of thing. So yeah, please do get as involved as possible. Hopefully you've got the slides downloaded already. If not, they're in the description somewhere. So please feel free to download them. And let's get started, I reckon. So for those of you, oh, this is where my thing is not going to work properly. There we go. So those of you that haven't met me yet, I'm Alyssa. I'm the lead GCSE chemistry teacher, and I also teach A-level chemistry for SnapRevise. I've got a PGC in chemistry education from Oxford University. So I love science, chemistry being my favourite, but I teach all of the sciences. And I've been teaching A-level chemistry for the last 6 years and tutoring it and stuff. So very much enjoy science. Science is my thing. If you are interested in trying SnapRevise, our kind of more complete course, then we do have a discount code for you to get 1 week free. So if you wanted to come along, we're starting our full timetable as of next week, I believe. So you can come along and check out the full timetable then. So if you want to try the code Lattice7, LATTICE 7, if you type that in at the checkout, then you can get 1 week free trial, and we've popped the discount code in the chat as well. So if you'd like to try it, then please do have a go, see what it's like, and I'll talk a little bit more about what we offer in the tutoring package at the end of the class. I'll show you around the website a little bit as well. So okay, so what we're hoping to do in this session, or hopefully what you guys are going to get out of it, is we're going to understand lattice enthalpy and what it is. So it's a measure of ionic bond strength. We're going to look at doing Born-Haber cycles and how to construct them. And we're going to look through, there's a lot of key phrases, keywords, definitions that we need to be very, very comfortable with. So if you're not, then that's fine. Just make a note to yourself that you need to do that. This is year 13 content, yes. So if you're not a year 13, please feel free to stay, because you've hopefully done things called Hess cycles. And Hess cycles are very, very similar, and the process is very similar, and there's a lot of content that overlaps. It's just this is another version of doing the same thing, basically, just a little bit more detailed, a little bit more intricate. And if Hess cycles is a hard concept for you, then doing Born-Haber cycles, it will be good, because hopefully you'll see it's one of those things when you're kind of at key stage 3, maybe even GCSEs, you think, oh gosh, this concept of atoms, this is mind-blowing. And then you go up to A levels and you're like, oh gosh, no, that's hard. The stuff I did earlier, it's not so hard. And hopefully you can have the same thing here. You go Born-Haber cycles, what the heck is that? Hess cycles, well, that's easy then, if that's all I've got to do. Hopefully you can have that sort of thing, maybe. But if not, it might help you, because it might help you put together some of the pieces of the puzzle that aren't quite that aren't quite fitting at the moment. Okay, and then we're also going to perform calculations using the Born-Haber cycle. What we're not going to look at, though, is polarization of anions, or the theory behind why different things polarize and don't polarize, and what the trends are in those. We're not going to look at any assumptions made in calculating theoretical lattice energy, and we're not going to look at covalent bond character either. So we're not going to relate this ionic lattice theory to covalent stuff. Okay, so again, if you haven't seen this kind of our lessons before, what we do is provide you with the spec points for the 3 different main exam boards, AQA, OCR, and Edexcel. Please have a quick read through, hopefully on your notes in front of you, as to what it is that your exam board is expecting from you. And if there's anything that doesn't make sense, or you'd like me to go through again in more detail, just let me know and we can go through it really briefly. But that's AQA. This is OCR. So this is the OCR spec points that we're going to be covering. Each of the exam boards give their specifications slightly differently. Edexcel tends to not have quite as much detail, but it tends to be quite specific. OCR can have quite a lot of detail in it. And AQA is kind of a mixture of the two. So have a look, check with your specification at what's expected of you, and then we will keep going. So I'm going to need to turn this over so that I can write on it. Oh, I just clicked forward and I didn't mean to click forward. Go back. There we go. So what do we already know? Can you give me some of the definitions here? First, ionization enthalpy and enthalpy of formation. So this is year 12 stuff. So if you're a year 12 student, hopefully you know what this is. Can you give me a description of either of those two? And also, if you know, or if you can guess, most enthalpies of formation, are they going to be exothermic or endothermic, do you think? So definitions of first ionization enthalpy, enthalpy of formation, and then whether or not you think enthalpy of formation is going to be mainly exothermic or endothermic. What do you think? And if you don't know the actual definitions of these things, the word for word definitions, then give me a description. What do you think the first ionization enthalpy is? What do you think the enthalpy of formation is, if you don't know? So pop it in the chat if you can. Give me one or t'other or both. Let me know what you think. If you had to guess, the other thing is that here I'm using the term enthalpy. You might have heard it as energy as well. First ionization energy, first ionization enthalpy. Lovely. So the minimum amount of energy required to move 1 mole of an electron from an atom in its gaseous state. Really, really nice, Iola. That's a fantastic answer. So I'm going to copy yours basically word for word. So the first ionization enthalpy, when we talk about enthalpy, normally it's because it's per mole. So we're talking about 1 mole. So it's the energy required to remove 1 mole of electrons from 1 mole of atoms in their gaseous state. Very nice. Now, my key hint for everything to do with Hess cycles and to do with Born-Haber cycles, when you're revising, when you're trying to do them yourself, is to learn the definitions and learn what they mean. So the fact that this is about gaseous state gives us a big clue and will be very useful in the future. What about enthalpy change of formation? What's the enthalpy change of formation then? This word gives you a clue, formation. So it's the energy required under standard conditions, because most of our energies and enthalpies are standard conditions. The energy required under standard conditions for 1 mole of a compound being formed from its elements, there we go, from its constituent elements in standard states. Very nice. So it's formation, it's forming something from kind of the basic building blocks of our elements. So it's the enthalpy change or energy change when 1 mole, and notice these are always 1 mole because they're enthalpies, so they're always talking about 1 mole. Enthalpy change when 1 mole of a substance is formed from its constituent elements in their standard states under standard conditions. So what this means, just a reminder, is things like if you're making nitrogen dioxide, you're making it from N2 and O2, because that's how we find nitrogen and oxygen in nature. We find them at standard states, under standard conditions, at normal atmospheric pressure and temperature and room temperature. We find nitrogen as N2 gaseous and oxygen as O2 gaseous. So those are our substituent elements of NO2, for example, at standard states under standard conditions. Okay, enthalpy of formation then, because we're going from kind of a basic form into another form, you can, it's not a very easy thing to kind of memorize, but basically almost every enthalpy of formation is exothermic. So I'm just going to put nearly always because it's not 100% of the time, but basically is exothermic. And therefore the reverse process, which we call dissociation, so formation and dissociation is therefore mostly endothermic. I say there are 1 or 2 exceptions that prove the rule, but nearly always exothermic. Okie dokie. Please, if at any point you don't understand my writing, you can't read my writing, which is totally understandable, please just let me know and I will tell you what it says / rewrite it. Okay. And if anybody has any questions, please just pop them in the chat and I'll keep checking. So part 1, lattice enthalpy and Born-Haber cycles. So let's talk about what these are. So lattice enthalpy. So again, if you've not met this concept before, you can pick it apart using the words that we're given. It's lattice enthalpy is the enthalpy associated with a lattice. So we can either talk about the formation of a lattice enthalpy or the dissociation of a lattice enthalpy. So bond enthalpies can be used to measure covalent bond strength. Lattice enthalpy is essentially the ionic bonding equivalent. So we talk about bond enthalpies when we're measuring covalent bonds. This is the ionic equivalent. And our lattice enthalpy of formation, so I'm going to start writing in some of our symbols, is how do you think, pop in the chat if you've got any ideas, how you think the lattice enthalpy of formation differs just from our enthalpy of formation. See if you can work out what the difference is. What are we forming that's different from the previous one? And when we do our symbols, we do change in, the delta symbol, which means change in, lattice enthalpy, LE, and the enthalpy is the H. And then our funny kind of like underground symbol means standard states and conditions. And this, again, is nearly always negative. It's nearly always negative. Any ideas how it might change? Well, if we're talking about lattices, we have to form, well, what do we have to be forming? we're talking about ionic bonding lattices. We're going to be forming, yeah, exactly. Well done, Lucy. Fabulous. We're going to be forming a lattice. We're going to be forming an ionic lattice, so an ionic solid. So lattice enthalpy is the enthalpy of energy change. Oops. When, now this time we're going to say it kind of the other way around. Exactly, because we're forming a lattice, and because we're forming when 1 mole of gaseous ions form an ionic solid. So our ionic solid or our ionic lattice is what we're forming, and dissociation is just the same. Oh, it should be, oh no, I've got that in the wrong place. When gaseous ions form 1 mole of an ionic solid. Of an ionic solid. So I've got that the wrong way around. So lattice enthalpy of formation is forming 1 mole of an ionic solid, and lattice enthalpy of dissociation is, funnily enough, when 1 mole of our ionic solid dissociates. And again, we can pop the same symbols in. If when you're doing this in an exam, you want to put lattice enthalpy form and lattice enthalpy dis, that's fine. But to be honest, as long as you've got your positives and negatives the right way around, your examiner should know which is which. So it is the enthalpy change when 1 mole of an ionic solid dissociates into its gaseous ions. Fantastic. Okay, so that's kind of definitions of lattice enthalpy. I'll say again, it's really important, I think, when trying to do Born-Haber cycles and Hess cycles, that you really get to grips with what the definitions mean or what they're talking about, because otherwise you will find it incredibly difficult to create and fill in these lattice enthalpies. You won't know these Born-Haber cycles and Hess cycles, because you won't know what needs to go where. You won't know what else you need to add in, or how to link the information together. So it's really important that you learn what these are. And if you're not very good at learning things, pop them on a flashcard and test yourself, or do copy, cover, repeat, or get somebody else to test you, or try and explain it to a family member to help yourself to understand and remember which is which. Okay. So let's have a look at Born-Haber cycles then. So what we've got here is an example of a Born-Haber cycle. So lattice enthalpy is a combination of multiple energetic changes, in the same way that with a Hess cycle, Hess's law says you can take any, and the energy change is independent of the route taken. It's the same in a Born-Haber cycle. So this energy change here in blue is the same as all of these other energy changes. It's the same principle, exactly the same principle. We use Born-Haber cycles to describe these and make predictions about lattice enthalpy. It's very difficult to measure lattice enthalpy in a lab. Therefore, usually we have to go a really roundabout route just to try and work out what it is. So here, I'm going to do here. What am I doing here? I'm forming something from elements in their standard states. So anybody know what I can label arrow A as? I'm forming something from elements in their standard states under standard conditions. So what is this arrow, which I've labeled as A? What can I label that as? Anybody know? What can I label arrow A as? Yeah, well done, Ash, brilliant. Enthalpy, yeah, and Lucy, brilliant. It's the enthalpy change of formation, which we show with an F for formation. Yeah, well done, Iola, and blue light as well, brilliant, fantastic. Standard enthalpy change of formation, fantastic. B and C are these next two, which look very similar, and this is where I think this is a bit of a puzzle solving mission. What can you see that's different between this point 1, and point 2? What's changed? What's happened to go from point 1 to point 2? Can you see a difference? What's happened? Well done, Catherine and Maze as well. Yep, well done. What's happened to get from 1 to, yeah, a state of which, Iola? Yeah, good, exactly right. Well done. State of sodium. Sodium's changed to a gas. Fantastic. So what has happened is my sodium has changed to a gas. Does anybody know what we call this? Ah, fantastic, Catherine, you've nailed it. Yep, and what on Maze as well. Atomization. Good. So it's the atomization of sodium at B, and then again, what's happened between 2 and 3? I mean, we can guess because I've told you that B and C are the same, but what has happened and what can you see the difference here? What's the difference that's happened? So we can basically ignore sodium now because we know that that stayed the same. What's happened here? Yeah, the chlorine. We've gone from Cl2, which is how you would find chlorine in its natural state. We've had to split. Yeah, good. It's ionization of chlorine. Well done, Nanking, exactly. We've split the chlorine. So it's no longer in a pair, which is how it should be, which is how it's most stable. We've split it. We've atomized chlorine. So it's atomized chlorine. We've gone from Cl2, where it's in a pair, to chlorine, and we've put a half in there because we only want half of Cl2. We only want 1 chlorine atom, so we have got 1 chlorine atom. Good. So these are both enthalpies changes of atomization. And so again, we need a definition for it. This is the enthalpy change when, funnily enough, 1 mole of compounds, oops, don't get rid of that, is broken or separated into its constituent, the constituent atoms, the atoms it's made of. Very nice. Good. Okay, so that's A, B, and C, which I need to label there. Okay, let's keep going around though. What's the next step going to be? If that's A, B, C, what's D? What's this step? We're going from this, 2 things in the solid, in the gaseous state, to this. What have we done? What's happened at D? Oh dear, apologies. What's happened at D, guys? Does anybody know? Oh my gosh, well done, Geraldine, fantastic. Yep, and Catherine, brilliant. We've ionized sodium, good, well done for noticing. We've turned a normal sodium atom into a sodium ion and its electron. Very nice. Whoops, didn't mean to do that, I meant to rub out. So D is our ionization. And it'll be the first ionization energy, so we usually call that IE1, ionization energy 1 of formation. So I'll just put that ionization. So we've already defined that one, we know what that is. What about this step then? What about going from 4 to 5? What's happened there? What have we done there? Ah, really nice. You guys are ahead. You're ready. Fantastic. So it is the first electron affinity. This is our chlorine accepting that electron, and we call that electron affinity. How do we know it's ionized and oxidized? Oh, as in how do you know the difference between whether it's been ionized and oxidized? Well, actually, technically, a lot of the time they are the same thing, because we have lost an electron, so it has been oxidized, but the process, I think we would describe it as being ionized. The process is ionization. The element itself has been oxidized. I don't know if you can see there's a slight difference there. The process is ionization, the removal of an electron, and we can talk about that thing as being oxidized. It has been oxidized. And yes, you can talk about chlorine gaining electron or being reduced. The process, especially when we're using Born-Haber cycles, when we're trying to label these, the process, we talk about it as being ionized and the electron affinity. So let's give that. So this is electron affinity EA. And again, because it's the first electron affinity, we give it a 1. and its enthalpy. So this is electron affinity. So again, we're going to need affinity. We're going to need a definition. Affinity, can't spell. So that is the enthalpy change when, and you can probably guess how much, is 1 mole of gaseous atoms gains 1 mole of ions, or is converted to 1 mole of ions. That's supposed to say atoms. Is converted to 1 mole of gaseous ions. You can talk about gaining 1 mole of electrons as well. That's absolutely fine. Actually, let's give it a charge as well. Gaseous 1 minus ions. Great question. How do we know the difference? Yes, Nafisa, I would agree with that. What's the difference between atomization and ionization? What can you see the difference? So atomization is kind of this, for example, going from an element in its solid state to a single atom on its own in the gaseous state. That's our atomization. We're going from, because I know it's very difficult to think about it, but like sodium metal, whenever we say Na, we're talking about a lump. We haven't defined how much, we're just talking about a lump of metal, which is actually hundreds of atoms. Hundreds of thousands of billions of atoms. What this process is going, what B, the arrow B is going from sodium, a lump of solid sodium, to 1 single atom. We're trying to separate each thing into a separate ion, a separate atom, sorry. That's atomization. Ionization is turning it from an atom into an ion. Okay, again, this is what I'm saying. Once you are confident with these definitions and what the difference of these means, it makes Born-Haber cycles and Hess cycles so much easier. Oh, cool. Let's keep going. Let's keep going. So that's another definition I'm afraid we need to know. Let's put some numbers in and have a go at a calculation. So lattice enthalpy for sodium chloride. So sometimes you're asked to fill in the Born-Haber cycles yourself. Sometimes you have to fill them in and then do a calculation. Sometimes you just have to do a calculation. It kind of depends. Here, we're trying to work out the lattice enthalpy, and again, this is where our definitions come in. We want the lattice enthalpy of sodium chloride. So lattice enthalpy is the formation of an ionic solid, which is this one, from its gaseous ions, which is this one. So although we've already got it labeled on this diagram, in an exam question, you might not have it labeled. You've got to work out which one it is. So if you know your definitions, you can work out which it is. It's the formation of an ionic solid from its gaseous ions. So that must be this red arrow here. So that's what we're trying to find, our lattice enthalpy. Like that. And because I'm doing the formation, because I'm forming the lattice, you might be asked to find the dissociation, in which case your arrow would go the other way, because the dissociation is it separating into its gaseous ions. Oh, Nafisa, you are quick. How have you managed to get an answer already? Haven't even finished talking about it. And Geraldine, amazing. Well, let's just double check that you're correct. You probably are. Let's have a go. So, same thing as Hess cycles. Instead of going, you can't go directly, because that's the point of us drawing them. So you have to go from the start of an arrow to the end of an arrow, but you can't go direct. So you have to go around the other way. So that means going against this arrow, going against this arrow, against this one, and against this one. So you might have been taught to do this slightly differently. What I do is I write that out as an equation. So my lattice enthalpy in this case is going to be, I'm going against this arrow, so minus 349. I'm just checking that I'm still doing 1 mole of everything, because it sometimes can be funny. So I've got 1 mole of that, minus 1 mole of my other one, minus my plus 122 minus plus 496. If anybody notices me make a mistake, please do call me out on it because it has been known to happen. Where am I now? Minus plus 107. And again, minus, but, oh no, it's plus that one. Plus, because I'm going with the final arrow, plus minus 411. And this is where we need to get our calculators out just to double check that we're happy. And we should have a number that comes out as minus 787. And these are all in kilojoules per mole, even though we haven't said, but it is in kilojoules per mole because they're lattice, they're enthalpies. So we'll be in kilojoules per mole. Fantastic. Now, obviously, you can go through, you can take it slowly, you can work out what each of them are, but that's the basic premise. Anybody not happy with that? How is everybody feeling? I've gone through that one quite quickly because we've got a complicated one coming up, so we're going to go through that a little bit more slowly. That's the basic premise of working out lattice enthalpies or missing bits. You know, it might be that you're given the lattice enthalpy and they want you to find out the atomization of chlorine or something. Depends what they're asking. So if anybody's got any questions, please ask. Otherwise, can you just pop in the chat how you're feeling about lattice enthalpies and Born-Haber cycles? Give me a 1 or a smiley face if you're feeling, yeah, that's pretty straightforward actually. I'm not so terrified about that. 2, if it was all right, I might need to go over it again, not feeling so good, but you know, it was okay, we'll cope. And 3, oh my gosh, no, I'm gonna have to go over this like 8 times. That was horrible, I hated it. Just let me know in the chat how you're feeling. Yeah, Maze, so that one was us finding lattice enthalpy of formation. It was forming, because the arrow went down from the gaseous ions to the solid, so it'd be forming. Good question, Mo. What would you do if there's a different number of moles within the same reaction? So let me have a quick look at my, yeah, we have a question for you. I have a question for you in the our next exam question. We'll answer that question for you, so we'll have a go. We'll come to that in a second. Lovely, no worries, that's absolutely fine. Yeah, absolutely, all good, guys. No, that's all good. Thank you very much for sending that, fabulous. Okay, so let's have a go then at doing these questions. Yeah, Catherine, like I know lots of people struggle with the kind of the what's the term? The detaily bits, and just double checking they're confident about what one thing is versus the other. Especially if you're given a weird one in the middle, because you've got, you know, it's harder then, I think, often harder to form the Haber cycle. But if I just flick back, I'll go to a different color. Let's go light blue. No, let's go orange. So if, for example, they hadn't given us this number and we had to try and find this number, which is our atomization of sodium. It's sodium going from a solid to a gas, atomization of sodium. They wanted us to find that. Start the beginning of the arrow. This is where you've got to be confident in definitions, because the arrow's got to be pointing upwards. It's got to be going from a solid to a gas. That's the atomization, is going from a solid to an atom. So start at the beginning of the arrow, end at the end of the arrow, and go back around the cycle the other way. Start from the beginning, end at the end, but go the other way around, and then just check. Okay, so in this case, I would be going with that arrow, so I add that value. Then I'm going against the lattice enthalpy, so I would then need to minus the lattice enthalpy value, whatever it was. Then I'm going against that arrow again, so I'm going to need to minus whatever that value is. I'm going against that one, so I'm going to need to minus that one. I'm going against that one, so I'm going to need to minus that one, and that should give me my answer. So it's the same process, it's just using different numbers, that's all. I'm just going to get rid of my yellow just so that it's not quite so confusing. And you should hopefully get, if you practice this one, you should hopefully get 107, positive 107, hopefully. So go back and have a practice. Do that one. Now we know what the lattice enthalpy is because we've just worked it out. Have a go at working out all the others and just double check that you get the numbers that are written on this cycle for each of them, because that's very good practice. Very, very good practice. Okay, Cool, right, let's have a go. How are we doing for time? Good, we're doing well. So this question says, the lattice enthalpies of sodium fluoride, sodium chloride, and magnesium fluoride are shown below. Explain the differences between these lattice enthalpies. So now we're going back a bit to think about what the lattice enthalpy means and how it can change, or what can change it. Yeah, so awesome. This is what we're doing here. Good question. This is what we're doing here. We're talking basically, so lattice enthalpy is our ionic equivalent of a bond enthalpy. So we are talking about the strength of the bond basically between the two ions. So it's going to be very difficult for us to compare sodium chloride and magnesium fluoride because they are completely different to each other. But we can compare sodium fluoride and sodium chloride because we can compare the fluoride and chloride ions to talk about why that might mean that our lattice enthalpies are different. And we can compare sodium fluoride and magnesium fluoride because then we can compare the cations. And again, that might tell us why these two numbers are different. So does anybody have any thoughts? Let's do the first two first, sodium fluoride and sodium chloride. What's different about fluoride and chloride that might mean that the lattice enthalpy of sodium fluoride is a larger value? Does anybody know? What's different about the fluoride ion versus the chloride ion? Does polarity play a part? Considering at the moment, when we talk about polarity, we're mainly talking about covalent bonds and how polarized a covalent bond is. We probably wouldn't mention polarity when we're talking about an ionic bond. It's a good thought. Yes, and yes, fluorine is more electronegative. It is more reactive, definitely. But I'm thinking more about, yeah, good size. Fantastic. Yeah, well done. Lots of you have got that now. Good. We're talking about size. So which is bigger, a fluorine or a chlorine? Hopefully we're aware chlorine is bigger. It's got a whole shell more. So a chloride ion has a larger atomic radius. Whoops, I can't spell today. Has a larger atomic radius. What do you think that means for its ability to bond with sodium then? And if we're not sure, we've been told which is better. So which is going to have a bigger attraction to its sodium counterpart, fluorine or chlorine? We've been told, we've been given the details, the data. The only thing you needed to know was the size difference. So chlorine is larger, fluorine is smaller. So chloride has a larger atomic radius than fluoride. Therefore, we can see from the data, it's got a less, there's less energy given out when they bond. Therefore, it must have a weaker attraction. Fluoride has a bigger attraction. Exactly right. So chloride ion, you can say it either way around. I've just gone with chlorine, doesn't matter. So chloride ion has a larger atomic radius than fluoride, therefore has a weaker, oops, that's rubbish. Weaker attraction to sodium ions and hence a lower enthalpy. Well, good point. We haven't actually put marks on this question. It would probably, I'd say 4 marks, probably. One for your, one for each difference and one for each explanation. So I'd say 4 marks probably. So no, it's not easier for fluorine. You get more energy given out when you make the bond. That means you have to put more energy in to break the bond. You can think about it in both ways. My brain works so much better thinking about breaking bonds. So the lattice enthalpy of formation is going to be -918, but the lattice enthalpy of dissociation, breaking the bond, will be the same value, but in positive. Lattice enthalpy is the energy of an ionic bond. Does that mean I have to provide that energy to break the bond? So if you're talking about dissociation, Orson, this is to answer your question. If you're talking about dissociation, yes. You're talking about formation, no. Formation is exothermic usually, a bit like when you are putting two magnets together. When you're forming, because you can think about our positives and our negatives, they are attracted to each other. So to form a bond is going to release energy, because by forming this bond, by interacting with each other, they are becoming more stable. They're both gaining their full outer shell, they're both gaining their noble gas electron configuration. So they're going to be giving off energy and becoming more stable. Then if I want to pull them apart, I have to put energy in to pull them apart. Hopefully that helps. So chloride ion has a larger atomic radius than fluoride ion, therefore has a weaker attraction to sodium ions, and hence a. Now, this is where I try to be as specific with my wording as possible so that you don't end up accidentally contradicting yourself. So we can say a less negative lattice enthalpy, or less exothermic lattice enthalpy. Actually, I might change that too. It's probably a little bit more scientific. Less exothermic lattice enthalpy. So in my case, I'm talking about chlorine being larger than fluorine. I'm talking about chlorine having a less exothermic lattice enthalpy. Like I said, you can also do it in reverse and talk about fluorine being smaller and therefore having a greater attraction for sodium ions and therefore a more exothermic lattice enthalpy. That is also fine. So I reckon that would be worth 2 marks. The next part, we need to talk about this. Why is this magnesium fluoride huge? Why has it got a huge lattice enthalpy? And again, now we can compare the cations. We can compare the metal ions. What's the difference between them? Again, let's go back to the beginning. So what's the difference between them? And therefore, why is magnesium fluoride going to have such a higher lattice enthalpy than sodium? Okay, Mohammed, charge density. Why? What's the key? What can you tell me about sodium and magnesium ions? Aoran. I'm sorry if that's not how you pronounce your name. Yes, it is to do with that. Exactly, Lucy. Fantastic. Good. Magnesium forms 2+ ions, sodium forms 1+ ions. So because of their groups, and therefore, yeah, exactly. Awesome. Well done. Therefore, the charge on the ions is a lot bigger on magnesium than it is on sodium. That's the biggest difference. Agreed, there will be a difference in the atom sizes because they are different atoms, but the difference is going to be minuscule, absolutely minuscule. The biggest difference by a long chalk is the charge, the difference in charge. So Mg2+, and because it has a 2+ charge over one ion, and sodium has a 1+ charge over an ion, then Mg2+ has a greater charge. And therefore, talk to me about what it's going to do with the fluoride ions, or how can we talk about the attraction? Mg has a greater charge than Na+. Therefore, what do we know? Is it also to do with 2 fluorine ions? Yeah, so definitely there's going to be greater attraction. There will be a greater, I'll answer your question in a second. Greater attraction, let me just finish this. And hence a more exothermic lattice enthalpy. Nice. Yeah, so Ash, I was going to say, is it to do with 2 fluorine atoms? You could talk about it being to do with 2 fluorine ions. Sorry, I said atoms and I meant ions. You could. We're still talking about just the dissociation of a lattice. So yes, you've got 2 fluorines to dissociate, but we're not talking about per bond. We're not making a comparison per bond or per interaction. We're simply talking about per, like turning an ionic solid into its gaseous ions. So it's something that you can bear in mind, but in this case, lattice enthalpy is per mole of the compound, and it's separating 1 mole of the compound into its gaseous ions. So it doesn't really matter whether it's bonded to 2 or more ions, because it's still that amount of energy to separate 1 mole into its ions. Does that make sense? Cool. Could we think about enthalpy in this way? Energy is required to dissociate them, thus when they're brought together, the energy required to dissociate is no longer used for that purpose, and thus releasing the energy required to dissociate them. Yes. Yeah. Okay. Yeah, Mo, I like that. So this is the way that I think about things when people find it very difficult, especially at GCSE or GCSE level, to think about how something can go from being a solid to a liquid to a gas. And in order to turn it from the solid state to the liquid state, you give it energy, and the particles have that energy. And because they've got that energy, they can then overcome the interactions. So because they've got kinetic energy, there isn't kind of enough time for them to form their interactions with each other as they pass, and therefore we have liquids. And if you give them even more energy, then they do that, but as a gas. They whiz around all over the place, and as they come nearby, they've got too much energy, they're traveling too fast, they then don't interact as much and pass on. And it's a similar thing. If you force them to interact, i.e. force them to become, go back, change state back down to a liquid, they will release that energy, because the energy that they contained, perhaps as a liquid, or perhaps as a gas, to travel around, needs to go somewhere, so they become more stable. It's a nice way of thinking about it, actually. Yeah, I think it's got a good process there. We can just use the LE formula if we are, just the definition. Yeah, exactly. Yep. Sorry, Geraldine, why would there be greater attraction where? I'm just thinking we're going to need to move on in a second because we're running out of time. Nafis, I'm sorry, I'm slightly confused about that explanation there. Why are there a greater attraction for the Mg2 plus? Because it's 2 plus. Think about the ratio between protons and electrons. There are 2 more protons in magnesium than there are electrons, hence it's got a 2 plus charge. So it has a larger charge. It's got a stronger positive attraction than a sodium, which has only got a 1 plus charge. So there is going to be a greater positiveness for Mg2 plus than there is for sodium 1 plus. Kind of a bit like maybe if you had like a magnet that was on level 1 and then you turned it up to level 2. It's got a bigger attractive, I don't want to say force because it's probably the wrong word, nature to it. Okay, right, sorry, we're going to need to move on because I'm very aware we're slightly running out of time. This is probably going to take us longer than we realise, and I would like to go through a couple of things before we finish as well. So, okay. If I point out, so we've got letters A, B, C, D, E, F, and G. We haven't been given a value for G, so my guess is we're about to have to calculate it. So let's work out where all of these enthalpy changes fit in our diagram. It says write the correct letters from the table of data to label the Born-Haber cycle below. So I always, whenever I'm doing these, because I do, like they are hard, especially when you first get into them, find the ones you know and fill those in. So things like enthalpy of formation and lattice enthalpy, where do they fit? So enthalpy of formation in this case, we're doing sodium oxide. So enthalpy of formation, just normal enthalpy of formation is when it's in its elements in their standard states forming my substance. So standard states forming the substance must be, this is their elements in their standard states, not ions, not gaseous ions, standard states forming the substance. So this must be my enthalpy change of formation, F. Good place to start. The other one, again, this is our ionic solid. So the other one that's fairly easy to fill in is lattice enthalpy, because it's going from elements in their gaseous, or ions in their gaseous states to sodium oxide. Oh, that's a good idea, Nafissa. Very good idea. Let's do that. 1, 2, 3, 4. Oh, why am I doing it in this order? No idea. I've made it very confusing for everybody. I'm going around in a circle, anti-clockwise for some reason. Who knows? Well done, Nafissa. Very good. Yep. So give me some numbers then. Very good idea. Which goes where? Yes, G is to the right. Yeah, lovely. So 5 is going to be G because it's our gaseous ions becoming a ionic solid. Fabulous. Well done, Tarek. Good. What about the others then? How can we fill those in? How can we fill those in? They've given us all of the kind of the definitions that we need. We've used F and G. What are the other ones going to be? Think about what they're talking about. Think about any keywords that you can picture. And again, like this is a puzzle, I think. We can look at what you've got, look at what you ended up with, what's changed, and therefore what's the arrow representing. So 1 is D. Let's just check. So we're going from 2 sodium atoms to 2 sodium ions. 2 sodium atoms to 2 sodium ions. Hi, Khadija. What have we covered? So we've looked at all of the definitions, we've described them, and now we're filling in a Born-Haber cycle. 3 is D. Yeah, so here we're going from a solid to a gas. Good. So that one's D because that's the atomization. It's going from a bulk solid to individual atoms of sodium. We've got good, Geraldine. Fantastic. So 1 is we're ionizing ion. So it's got to be the first ionization energy. Ionizing sodium, sorry. Don't know why I said ion. So it's the first ionization energy of sodium. And Geraldine, you've recognized already that it's going from 2. And this is a key thing because we will probably forget that. So I'm highlighting it to us to remind myself it needs to be 2 lots of, because it's per mole and we've got 2 moles. What else haven't we done? Sorry, I'm trying to catch up on all the chat. So this one is going from oxygen. So that's the atomization of oxygen. So that must be E. So well done if we've put that in. 7, this is our oxygen gaining 1 electron. So that's the first electron affinity of oxygen. And then 6 is B with a second one. It's going from O minus to O2. Fabulous. Well done if you got those, guys. Really well done. Okay, now same process. You're absolutely nailing it. Fantastic. Same process, especially, yeah, guys, for people that have never done this before, you are smashing it. So same process. I'm going to do it in a different color just to make it easier. What we're trying to find, we're trying to find the lattice energy of sodium oxide, which we labeled as G. So start at the beginning of the arrow, end at the end of the arrow, go back round. Is there another electron entropy and gives free energy? There is a class and gives free energy. When it is, I've got no idea. But there is one. Oh, have I labeled something wrong? Oh, I have. Thank you. Yep, I put D again and I meant B. Good spot. Thank you. Yeah, well done. Oh, I've done it again. I've just renamed again. B. Yeah, well done. Good spot. So yeah, we're going back round. So we're going to go against that arrow, against that arrow, against that one, against that one, against that one, with that one. And then that was basically ending us up at the thing. So we're going to need to do, this is where it's good if you've got a calculator. Well done, Rebecca and Oren as well. You guys both noticed it, and Nero as well. Good spot. Fabulous. Oh, and Lucy and Geraldine. Yeah, sorry guys, I don't know what I did. I went wrong. So now we can do the same thing. You just need to plug your numbers in. So I'm going to label them up super quickly and write us a calculation. Please feel free to have a go at work out what is our answer then for G. So I'm going against that one. So I'm going against B. So minus 790, minus positive 790. And there's only one of them, so that's fine. I'm going against that one, so it's minus whatever A is, 141. I'm going against that one, but it's 2 of it. So it's minus 2 times C, which is plus 496. Oops, that's supposed to be a plus. I'm going against that one, which is 2, which is E, which is that one. So minus positive 249. I'm trying to speed up, it's not working. D is minus positive 108. And then F is plus minus 414. So my lattice enthalpy is minus positive 790, minus 141, minus 2 times 496, minus positive 249, minus positive 108, plus minus 414. What number have we got? Oh, I've got a slightly different value. That's not good, is it? Oh, guys, we're bananas. Because this is atomization of sodium as well. 2 times. We spotted it on one, we didn't spot it on the other. So we need 2 times that as well. Sorry, my fault, should have spotted that earlier. So that's 2 times 108. Yeah, Geraldine, sorry, that's the value I've got as well. Written down is minus 2520. Kilojoules per mole. Apologies, I should have spotted that earlier. So what happens when you're trying to speed through it. Okay, I'm very aware of the time. I am ever so slightly running late. Is anybody super confused? If you just haven't managed to get the right answer yet, just go through it again in your own time. You should have minus 252. So we multiply the energy value by the number of moles of exclusively the element denoted in the nth. Yes, this is, yeah, this is where our definition is. This change here is the enthalpy of atomization of 1 mole of sodium atoms. So in this case, we need to atomize 2 moles. So we have to have 2 times the enthalpy change. Same thing above. This is the ionization of 2 moles, but the definition of ionization is 1 mole. Tarek, does that answer your question as well? Exactly. Thank you, Mr. Hess. Oh, bless you, Bohemian. That's very kind of you to say. Well, come and join us. Okay, I'm going to have to speed on because we are ever so slightly running out of time. But feel free to watch that back again. Watch this class back again because you can have another go in a minute or in a couple of weeks and try it again. Especially if you're in year 12 and you haven't yet covered them yet. Hopefully, you can go through the stuff in class, ask all your questions, come back here, double check, go do these questions again. It's all good. Yeah, exactly, Geraldine, because there's 2 moles of sodium. Yeah, exactly. Lattice enthalpy is positive or negative. So lattice enthalpy of formation will be negative because exothermic dissociation is positive because we normally, whenever we talk about lattice energy, we're normally talking about formation. So it doesn't say assume it's formation. Well, in this case, the arrow is pointing down, so we know it's formation. It's going from our gaseous ions to the solid. Okay, right. Hopefully, we can now understand lattice enthalpy as a measure of ionic bond strength, super quick talking now, understand Born-Haber cycles, and perform calculations using the Born-Haber cycle. So please have a look at our other web classes. We've got another chemistry one coming up next week. Yeah, there we go. And then we've got maths, biology, and physics after that. So please set a reminder on YouTube, subscribe to our channel and everything. Then we can go, then hopefully you can come and see us in our other classes. We do offer A-level chemistry tutoring on the website, so I'm just going to have to get this up. So if this is something you're interested in, I am one of the main chemistry tutors for A-level chemistry. So the YouTube live schedule we just popped in the chat. We offer at least 4 classes a week, which is content and drop-ins, and I'll just talk you briefly what they are. We cover the full curriculum. We have really good handouts that you can take home, take away, use for revision, fill in. They're great. You can watch all the videos back again. So if you miss a class or you want to watch it again, they're there for you to watch. And there's the one-on-one support, either in the lessons or in the drop-ins. So if you're interested in trying this out for a week, please have a go, use the code Lattice7, and that will get you a week free just to try it out. And I think we're starting our full timetable, like I said, next week. And if I just pop this off, stop sharing that. Oops, this is where my laptop's going to go really slow. I'll stop sharing that so you get my face. Nice. And then start sharing. Ooh, where's my, there it is. Start sharing this one. You can see this is our website. If you navigate up here to tutoring, then when it loads, it's going nice and slow here. If you scroll down to the bottom, so I'm going to click on A-level chemistry, or whichever subject you're interested in, but obviously we're mostly interested in A-level chemistry because it's the best. Scroll down to the bottom. We have our examples, so you can watch back those examples. We also have the schedule, which shows you which classes we have recorded, and if you're part of the website, you can click on those. It gives you the link to the video and the PDF as well, so you can have a look at those. You can re-watch back classes, and if I just go up here, so we offer web classes every week, at least 2 web classes every week, and usually at least 2 drop-in sessions, so you get at least 4 classes a week for your subscription. And the drop-in sessions are probably the most useful bit of revision you could do, which is practice exam questions. And every week we'll go through at least 3 exam questions that you guys have requested. We will check, we go through the mark schemes. We will talk about different things that maybe different exam boards need. You guys request what you want. So if you're really struggling with Born-Haber cycles, we can go through a Born-Haber cycle question. If you haven't done bonding in a while and you want to go back over structures of simple molecules and their properties, then we'll do that. You just send an email to us. We give you the email address to send it to. And then we log it in and we'll just go through whatever exam questions you want to go. So really, really useful. So if this is something you're interested in, please have a look through the website, investigate, watch our YouTube, watch the videos, the free sample classes, and get in touch at hello@snapproviders.co.uk if you're interested. And we can have a chat. And yeah, the Lattice 7 discount code gives you a week free. So anybody have any last minute questions? When is the web class on organic, nitrogen chemistry, NMR and benzene chem? You'd have to have a look, Nafissa. As of September the 1st, the new schedule will go up for the next month or so. So you can have a quick look through, see if any of those are interested. Or if you flick back through previous months, you might be able to see the one you're interested in. I don't know off the top of my head, I'm afraid. I don't have the schedule on me. But any other questions, please send us an email at hello@snapproviders.co.uk and we will try and get back to you and answer all of your questions. And I hope to see you in a future web class. Otherwise, I will see some of you, hopefully maybe next Sunday for our next chemistry class. Have a lovely week. Hope you guys enjoy the rest of your weekend and summer holidays, and good luck with going back to school. And I will see you guys soon. Thank you very much. Cheers, everybody. Bye.